So now we have some tools at our disposal. We're familiar with our equilibrium constant Ka. We're familiar with Kw. We're familiar with pH. So all of this kind of comes together in how we use our equilibrium constants Ka and a future one Kb for bases. For now, we're just going to look at Ka, our acid dissociation constant. What can we do with it? How do we use it? Well, as we've said, it is an equilibrium constant. Okay, it's got that capital K, it's just got the little a to tell us that it's specifically for acid dissociation. We saw in a table earlier that most of our values are very small. And just like we did with our earlier equilibrium calculations in the previous lecture, we can use our ICE box, our initial change in equilibrium box, in order to find the concentration of hydronium ion at equilibrium. And if we can find the concentration of hydronium, we can find the pH of a given solution. So let's say that we've got benzoic acid. Okay, we've got a solution of benzoic acid. It has a concentration of 0.220. We want to know what should the pH be of that solution. Benzoic acid, if we went and looked it up in a table, would have a Ka value of 6.3 times 10 to the minus 5. So we have an equilibrium constant situation. We have an equilibrium reaction. We want to use our ICE table. So here's our reaction here. We've got our benzoic acid, C6H5O2H, plus water goes to our benzoate ion plus the hydronium. Now, if you didn't know what the concentration or what the formula for benzoic acid was, that's fine. You could still do this problem, and I could show you. You could just write HBz plus water goes to Bz minus plus H3O plus. Because the formula of the benzoic acid doesn't really matter. From the name, we know it's behaving as an acid, so we know it's going to give away an H+. The rest of it doesn't really matter. Okay, we know it's going to go from Bz to Bz minus, or whatever. We could have called it anything we want. Okay, so knowing the formula of the acid isn't terribly important if you are given all of the other information. All right, so let's continue on with our ICE table here. So we know our initial concentration of benzoic acid. It's 0.220 given to us in the problem. What we set up here in our ICE table, and go back a little bit, is just all of the species that play a role in the equilibrium. We've got our benzoic acid, our benzoate ion, and our hydronium. Okay, so our benzoic acid is 0.220. Our hydronium and our benzoate ions are 0 concentration at the start of the reaction. And now we let things react. Some of my benzoic acid is going to lose an H+. It's going to give it to the water to form hydronium and benzoate. How much? We don't know. So we use that as our unknown. So we're going to lose X amount of the benzoic acid. For every X amount I lose, I'm going to gain a benzoate, and I'm going to gain an H3O+. So I'm going to lose X of the benzoic acid, gain X of the benzoate, and gain X of the H3O+. So my equilibrium line, again, is just like adding all of these up. And so I have 0.220 minus X is 0.220 minus X. 0 plus X is X. 0 plus X is X. And now I have my equilibrium concentrations in terms of a single variable. And so I can now plug those concentrations into my Ka. And so I have, here I just use Ben minus as my my concentration here, or my chemical formula. So I just put Ben minus times H3O plus. So that's my benzoate and my hydronium from the reactants, divided by the benzoic acid, has the H on there. And so that's my reactant. So products over reactants. The concentrations of my products are X for the benzoate, X for the hydronium, and 0.220 minus X for the leftover benzoic acid. And that equation has to be equal to the Ka, 6.3 times 10 to the minus 5. Let's take that value over to the next slide here. Okay, ignore that little thing down at the bottom there. That shouldn't have popped up yet. That's all right. We'll ignore it for now. So we have our x times x over 0.220 minus x. So we could, if we had a good solver function on our calculator, plug this into a solver and get a value for x, because we can see that x times x is going to give us an x squared, and that means we're going to have a quadratic equation. Okay, well, there's another thing that we can do here. Notice that the value of the k is very small, 6.3 times 10 to the minus 5. This is a very small value. What this means is that in reality, I am converting very little of my original reactant into product. So little, in fact, that we are going to assume that the value of x is much less than 0.220. So we're going to say that 0.220 minus x is essentially equal to 0.220. It's an assumption. It's a mathematical assumption. It's an approximation. We're going to check the validity of the approximation at the end of this calculation. So, but by ignoring that x that's being subtracted from the 0.220, we greatly simplify the math in this equation, because now what we can do is just multiply both sides by 0.220 and then take the square root of both of those, and we end up with x is equal to 3.7 times 10 to the minus 3. Okay, so that's my concentration of H3O plus. If I take that value, plug it into my value for my, or it's in my pH equation there, negative log of H3O plus, I get a pH of 2.43. Now we do want to check to see, was my assumption up here valid? Okay, and what we can do is we take the value of x that we got, we divide it by the value that we would have subtracted it from, we multiply it by 100%. Here we get 1.6%. So we basically created 1.6% error in my pH calculation. If the value is less than 5%, we're okay with that as chemists. So your assumption is okay. If this had come out to be something like 7%, that means that this approximation would not have been valid, and we would have had to have left this x in that equation, gone through and solved the quadratic. We try to avoid that if we can. Generally, that doesn't happen if x is fairly small. If x starts, or I'm not the x, I'm sorry, if the Ka is fairly small. For Kas that are in the 10 to the minus 2, 10 to the minus 3 range, it can get a little bit iffy in there. Once you hit 10 to the minus 4, 10 to the minus 5, 10 to the minus 6, that assumption is pretty solid. Okay, so here's one for you to try. What is the pH of a 0.3 molar solution of hydrocyanic acid, HCN? It's got a Ka of 4.9 times 10 to the minus 10. So try that one on your own, and I will post a solution for that. Now we can go back the other direction as well. If we know the concentration of an acid, maybe it's an unknown acid, maybe we don't know what the acid is, but we know its concentration because we knew its molar mass from other studies we can do. We can make a solution of it and measure that solution's pH. So if I know the concentration of the acid and the pH of that solution, turns out I can go find the Ka of that solution as well. So we're still going to use an ice box, but here we're going to end up knowing a little bit more information than usual. So let's look at an example with butanoic acid. So here's our example here. So we have a solution of 0.055 molar butanoic acid. It's found to have a pH of 2.72. We want to know what is its Ka. So we know the pH of the solution after it's reached equilibrium. Now we want to know what the Ka is. A little bit of information on there. We just say it's a weak monoprotic acid. So we say it's a weak acid, so that tells us it will have a Ka. And monoprotic means that it's only going to lose a single H+. There are acids that can lose more than one H+, and sometimes that can interfere with the calculations. They become quite a bit more complex. So here we're just going to say 1H plus is lost. That simplifies what we're going to have to do here. Okay, so here's our reaction. Again, if you don't know what butanoic acid is, that's okay. But we have our but H, that's our butanoic acid, plus water goes to but minus plus H3O plus. Let's put in what we know. We're just going to set up our icebox the way we always would, and then we're going to go back in and fill up some stuff a little bit later. So we have our 0.055 butanoic acid. I got lots of water. A lot of times I'll just write lots because we don't really care about the water. If you don't write anything there, that's fine too. Before equilibrium starts, we have 0 of the butanoate ion, the but minus, and we have 0 of the H3O plus. Okay, how much is going to dissociate? We don't know. We're going to call that minus X. So I'm going to lose X amount of the butanoic acid. I'm going to gain X amount of the butanoate. I'm going to gain X amount of the H3O plus. Again, because I have a 1-to-1-to-1 stoichiometric ratio, which is normal, these X's are all going to be minus X, plus X, and plus X. You just have to keep track of what's minus and what's plus. So, but because I have none of this to start and none of this to start, the reaction has to go in the forward direction to reach equilibrium. So at equilibrium, our E line here, I just add everything up. So I have 0.055 minus X. I still got lots of water. 0 plus X is X. 0 plus X is X. I can put that into a Ka expression, but we're going to look at something a little bit differently with this one. Now, since we know the pH, and why do we know the pH? Well, because they told us what the pH was in the problem. Because I know what the pH, I know the value of the H3O plus ion. I can calculate H3O plus from the pH. And if we look at our icebox, we see that the concentration of H3O plus at equilibrium is equal to the value of X. So let's use that information and solve our problem. So H3O plus is equal to 10 to the minus pH. So that's 10 to the minus 2.72. And we get a value of the hydronium ion concentration of 1.91 times 10 to the minus 3. Okay, and again, that is also equal to X. So now I can take my icebox, and wherever I had an X, I can plug in that value of 1.91 times 10 to the minus 3. So I have minus 0.0019 there, plus 0.0019 there, plus 0.0019 there. And so now I have my concentration of butanoic acid, my concentration of butanoate, and my concentration of H3O plus. I know all three of those. I now plug those into my Ka expression, which is still going to be products over reactants. So I have the butanoate, H3O plus, and my butanoic acid. When I calculate all that out, I get a value for the Ka of 6.84 times 10 to the minus 5. So that finishes out this part of the lecture. Kind of some weird calculations in there. Hopefully it's fairly straightforward for you, but as always, if you have any questions, contact me.